All right, so today we are talking about sets. We're in a new unit, sets and probability. And so we're starting off with the whole idea around set theory, basic set theory, because you need to know these different things in order to be able to do probability when we get to it. So today you're going to be able to recognize different set notations as well as apply them to Venn diagrams. And I think everybody remembers what a Venn diagram is, okay? But basically use sets and set notation to basically investigate fair games and how the idea of fairness relates to the probability of winning or losing. Okay, so when we actually get to probability, we might be looking at, a situation where there's a game and you're trying to determine, what's the probability of getting this particular type of hand if you're playing poker or anything like that. Okay, so we'll look at like different situations. And in order to determine like these different probabilities, you're going to need to understand the fundamentals of probability theory. Okay, now I know we can pretty much use logic and intuition to try to figure some of these things out, but at the end of the day, and sometimes that's helpful, but at the end of the day, it does fail at times, and you need to be able to rely on the theory of probability to truly understand why the probability of something happening being, what it is, true to what it is. You got to use the numbers, you got to use the math to actually make it work. Okay. So we're going to start off with set theory before we get to probability theory and the basics. Okay, a set is a collection of objects. Okay, and these objects are called elements. We kind of pretty much already dealt with sets a little bit when we're dealing with set notation. The part that was a part of the set notation would be called your elements. And so as you see in the black, these are your different types of numbers that you can have. This is reviewed from the very first unit, numbers in algebra. Remember the R meant real, the Z meant integer. Hopefully you're already answering these before I'm writing them down. The N means natural, and the Q means rational. Okay? Real, that's any real number, any number that we deal with. Integers, those are your positive and negative whole numbers, including zero. The natural numbers are your counting numbers, so that's 1 till infinity, 1, 2, 3, 4, 5, etc., etc. And rationals are any numbers that can be written as fractions. And as you see here, A through H, you don't have to write these down, but when I go over some vocabulary, I am going to use these different examples to kind of support some definitions, okay? So, here's the different types of sets. If you look, D and E, F, G, and H are all written in the set notation that we've dealt with before, et cetera, et cetera. Now, here's some vocabulary that we're going to cover. A precise set, N of A, empty set, finite set, and element, okay? So, a precise set is a set that is exactly a set that that really is defined. If you look at the examples that we have of D and H, those are examples of sets that are not precise. And the reasons why is because they don't specify what sort of numbers the set elements should be. Okay, if you look at D and H, really and truly, all you're looking at is the set of X values that are in between 0 and 5, or the set of X values that are less than 200. It doesn't say that they're integers or your rational numbers or just your counting numbers, et cetera, et cetera. So D and H, those two sets will be examples of sets that are not precise, okay? In order to make it precise, what would need to be added would be something like X is an element of integers. That way you know, okay, I know exactly what the numbers are. So you can almost sit and think like a precise set is something where you know exactly what type of numbers you're looking for that are a part of the set. So like A would be an example of a precise set. B would be an example of a precise set. Even G would be an example of a precise set because you can figure out what these square numbers are that are less than 50. Okay? The next one is N sub A. Now this N right here, this N means the number of elements in set whatever. So whatever's in the parentheses, that basically is asking you, what's the number of elements in set A. Okay? So if you look at N of A, what are the number of elements In A, well, you would say the number of elements in set A would be 5, because there's 1, 2, 3, 4, 5 elements there. The number of elements in set B would be 4, because you have 1, 2, 3, 4. Okay? If you look at G, N of G, the number of elements in set G, even though they're not listed, you can figure them out. What are the square numbers that are less than 50? Well, that's 1, 4, 9, 16. These are your perfect squares, 25, 36, and 49. I could write them out like this instead, and that would be 7, because there are 7 objects, 7 elements. Okay? Hopefully that's good. Now, if you try to do that for F, okay, N of set F, what are the number of elements that are in set F? Well, if you look, the set of P values such that P is a prime number and a multiple of 10. Well, if you remember from your definition of what a prime number is, prime numbers are numbers that are only divisible by 1 and itself, okay? And if a number is divisible by 10, then that means that it's not prime. So the number of elements in F would actually be 0, because there are no numbers that are prime numbers and are multiples of 10. F would also be called an empty set, because there are no numbers that fit this particular stipulation. So an empty set, which is our next vocabulary word, can be written like this, so basically like a 0 with a slash through it, or it can be written with curly brackets with nothing in between them. Those are the simple notations for empty set, okay? And that's basically when you have a set that has no elements, okay? Now, there's a big difference between this and having the curly brackets here. This is basically saying that your set has an element and the element is 0, okay? So like 0 is the number that's a part of the set. So this and this are two different things, okay? They do not mean the same thing. I don't want anyone to be confused there, okay? Now, finite sets are sets that contain finite number of elements. So that means they have a specific number of elements. So it's very close to a precise set because we know exactly how many elements we have. So finite set, precise set are pretty much like the same thing. So if you look at our examples A through H, which sets would be finite sets? Well, that would be A, that would be B, and that would be G. Okay, they're all examples of finite sets. Okay? And an infinite set would be a set that continues on and on forever. Okay? I mean, it's pretty much the opposite of a finite set. That would be something like D in the sense because it's just reading any numbers that are between 0 and 5, so that's including every possible real number, every decimal, every irrational number, etc., etc. Okay? So hopefully you guys understand those vocabulary words. And of course, elements are the particular numbers that are in the set. Now, elements don't necessarily have to be numbers. Okay, in A, yes, the elements are 1, 2, 3, 4, and 5. In B, the elements are 4, 5, 6, and 7. However, for C says that names of students absent from school. So, elements could also be names of people. They could be the names of the months of the year. Whatever the set is describing, whatever the set represents, those are your elements. So they could be numbers, but they also could be names as well. Okay? Now, Venn diagrams. Venn diagrams, I'm pretty sure you guys have dealt with, but we're going to be looking at not so much your classic Venn diagram where it's just the two overlapping circles. We're going to be looking at some that are concentric, where one lies inside the other. We're going to be looking at some that don't even intersect at all. We're going to be looking at a whole bunch of different ones, okay? But not all of them today at one time. We're going to, divide it up. But whenever you draw a Venn diagram, you need to define the universal set, okay? The universal set contains those elements that are under consideration. So whatever problem we're looking at is basically the universal set. The universal set is denoted with the U and must be stated to make a set well defined. So if you ever have to draw a Venn diagram yourself, you must include this rectangle with the U labeled. Without it, it's incorrect. Okay, the U with the rectangle represents the universal set, which is whatever situation we are considering. So anytime you draw a Venn diagram, you have to make sure that you include the rectangle. Okay? Now consider this problem. It says we are considering the months of the year that begin with the letter J. The universal set U would be those months of the year that begin with the letter J. So that would be January, June, and July, as you see there. Now, we're going to let set A be defined as the set of all months which end in January. Okay? What would this Venn diagram look like? So if anything, you need to treat the universal set like an umbrella. Okay? So the universal set is like the umbrella. Underneath the umbrella are the individual sets, such as set A, which defines the set of all months which ends in January. What would this Venn diagram look like? Well, one, you definitely need the rectangle and the U to represent the universal set. And inside it, you need to have a circle that represents set A. The circle is all the months that end in January. Well, out of the three that we have, that would be January. Then June and July, even though they don't end in January, they are still a part of the universal set. So they will be outside the circle. And what would that look like? It will look just like this. You have your rectangle, you have your circle to represent set A, and you have the elements that fit that particular type of set. The ones that don't fit that set, but are still a part of the universal set, would be inside of the rectangle. Now, someone asked me in class, like, well, what about February? Yes, February does end in a January, but it's not a part of the universal set, which says, we're looking at the months that begin with the J. So February is not even a part of this universal set because it does not start with the letter J. I hope that makes sense. Now, A is an example of a subset of U. Okay? Now, a subset is basically is a set that is a part of another set. Okay? It could be a universal set. It could be, an individual set. Okay? And so we're going to look at that a little bit more in detail in our next slide. Okay? Now, every element in a given set M is also an element of another set N. Then M is a subset of N denoted with this notation. Okay, it's like an elongated C with the bar underneath it. Now, if you're like, okay, well, what exactly does that mean? So let's say you have set M, and set M's are the numbers 1, 2, and 3. And then you have another set N, and elements of that set are 1, 2, and 3. Well, then M would be a subset of N because it contains every element that's in M is also in set N. Okay? So those would be subsets of each other. M and N would also be considered an identical set because they have the same number of elements and the same types of elements. Now a proper subset, which is just the elongated C without the bar underneath it, is a given set is one that is not identical to the original set. So a proper subset would not be two sets that are identical, okay? However, every element of one set would lie in the other, but only some of the elements in one would not lie in the other. So what does that look like? Well, let's say that M is the set of, it's a set that has 1 and 2, and N has the elements of 1, 2, and 3. M would be a proper subset of N. It'll be a proper subset of N because every element of M lies in N. So 1 is in N, 2 is in N. However, there are some elements in N that do not lie in M. That element would be 3. 3 is a part of N, but it's not in M. So that's an example, a very basic example of a proper subset. Now let's go ahead and let's look at some examples to apply some of this vocabulary. It says, let U equal the number of months in the year that end in birth. And then in part of that universal set, set A is going to be the months that begin with a consonant. B are the months that have exactly 30 days. And we're going to draw Venn diagrams to show that sets U. We're going to draw 3 different Venn diagrams. The first one has sets U and A. The next one has sets U and B. And the third one has all 3 sets. Okay, so I'm going to do each of these in different colors. Now, if we're going to draw sets U and A, well, anytime we draw a Venn diagram, we want to make sure that we include the universal set, which is the rectangle with the U. And again, a part of this universal set are going to be the months that end in birth. That's September, October, November, and December. But if we want set A to be included in part of this universal set, then we want the months that begin with a consonant. Okay? The months that begin with a consonant that also end in ver are September, November, and December. They all begin with a consonant. The only one that doesn't begin with a consonant is October, but it still is a part of the universal set. So it goes outside of the circle, which represents set A, but still a part of the universal set. We wouldn't include August, we wouldn't include April, we wouldn't include March, because those are not a part of the universal set. They do not end in ver. Now for the next one, we have the universal set and B. Okay, so we need our rectangle with our U to represent our universal set, and now we need a circle that's going to represent B. Now B represents the months that have exactly 30 days. Now if you do not know which months have 30 days, and you gotta look at the calendar to figure this out. Somebody said there's like a knuckle trick. Well, I really don't know the knuckle trick, and it's also gonna be kind of hard to explain through a video, but I know this little rhyme. Well, kind of a rhyme, but whatever. I learned that the rhyme goes 30 days past September, April, June, and November. All the rest have 31 except for February. So 30 days past September, April, June, and November. So that means September, April, June, and November all have 30 days. So out of the ones that fit our universal set, it's going to be September and November. Both of those have 30 days. All the other ones, October and December, have 31. They still are a part of the universal set because they are the months that end with birth. And the last one, we're going to draw all three together. So, of course, we need our universal set. Now, if you're thinking, okay, we're going to draw A and B like this, okay? You know, A, B, like the classic Venn diagram. Not quite. If you look at sets B and set A, okay, from the other two examples, don't all the elements in B also lie in A? Yes, they do, okay? Both September and November are part of set A, which means that B is a proper subset of A, because all the elements in B lie in A, but not all the elements in A lie in B. If that's the case, then what we're actually going to draw is a circle that's within another circle, okay? Because all the elements,
Miss Alexander,
all the elements in B lie in A.
John.
So we would draw this like so, because all the elements in B, September and November, are a part of A, and we still have that one month, which is December, that's a part of A. October is still the one left out in the universal set, but it's still a part of the set, no less. Okay? I hope you guys are okay with this. Now, empty set, which we've already talked about, which is the symbol with like the circle with the slash through it. An empty set is a subset of every set. Okay? I know you're probably like, wait, what? But think of it like this, right? If you have, say you have a set, let's call it W, and it represents all of the set of X values such that X is a factor of 20.
Good morning, Miss Alex.
So W would be the following elements: 1, 2, 4, 5. Oh my
Nicole,
God. So 1, 2, 4, 5, 10, and 20 would be the elements that are part of set W because they're all factors of 20. Remember, factors are numbers that go into the number evenly. Okay? Now, the empty set is a subset of W. Okay? Since every element of the empty set is in W, think about it. What's a part of an empty set? What numbers are a part of an empty set? Nothing, right? So realize that if a set has nothing in it, it's going to be a part of every single set. Okay? So an empty set is always a subset something in it, then that means it's going to be a part of any and every possible set. Okay? The other one is that every set is a subset of itself. So if we look and we're trying to determine, let's say we have something like this, right? And we're trying to determine if this statement W is a subset of W. If we're trying to determine that that's true or false, well, that would be a true statement. Because if you think about it, what are the elements of W? 1, 2, 4, 5, 10, and 20. Well, 1, 2, 4, 5, 10, and 20 are a part of W. So these are kind of like these two things here. They're kind of like theories a little bit, things that you accept. And I'm not saying that you'll be tested on this, that you'll be expected to know this, but it's kind of like one of those, like extra little add-in type things that go along with sets. So I want to make sure to address those here. Continuing on with Venn diagrams, you have some new vocab. You have intersection, which is like a upside down U kind of, more like an arch. This basically means that when you have two circles that intersect each other, like your classic Venn diagrams, the intersection is basically what A and B both have in common. Okay, so A and B both share.
Alexis Ramos.
They both share this common space right here. So if we had to write this in a sentence, we would say that A intersects B. So it's basically what the two sets have in common. That means intersection. Let's look at an example where intersection is applied. You have these 5 different sets, okay? And we want to write down the sets for A intersection of D. So we're going to write down 4 different sets. A intersection D. So that's basically asking you, what do A and D, what do those two sets have in common? Well, if you look, both A and D have 4 and 5 in common. So what's the set? 4, 5 with curly brackets. So what do these two sets have in common? I want you guys to answer B, C, and D. Pause the video and then press play when you want to see the answers. So press pause. All right, hopefully you figured out the rest of them. B, it says A is the intersection between, it's the intersection between A and B. What do these two sets have in common? Well, they actually have a few elements in common. They have 1, 2, 3, 4, and 5 in common. The intersection between D and E. Well, E is a square number less than 50. Remember that was 1, 4, 9, 16, 25, 36, 49. Almost missed that one. So the only one they have in common is 4. Yes, you can have sets that only have 1 element. And then what about C and D? What do they have in common? Well, considering that C is an empty set anyway because there are no prime numbers that are multiples of 10, this one is an empty set, or you could write it with the brackets that have nothing in between them. Hopefully you guys did okay with that. Union. Union is the U that points up. And so it's the arch that points up. The union is basically what, it basically includes all the elements in A, all the elements in B, or was in both. Okay, so as you look, this is the shaded region. Union would be all of this, okay, with both circles have in common. Everything that's in A or B or both of them. That will be written as A union B. Sometimes you'll be asked to shade, these different types of sentences, like what I just wrote down in the pink. And so you have to make sure you understand what union means and what intersection means. So again, intersection means that what they both have in common, and then union is everything from both sets. All right, let's look at this one, okay? All right, I want you guys to pause the video. I want you guys to give it a whirl, okay? You're writing down the sets. What sets are part of A union D, A union B, C union D? And I want you guys to write those down, okay? Pause the video. All right, I hope that we're ready to check this out. Hopefully you got that. What do A and D both have in common? Well, they have 1, 2, 3, 4, 5, 6, and 7. And maybe I shouldn't use that word, what they have in common, but more of like, okay, what elements are in A, what elements are in D, and what elements are in both. If you notice, they both have 4 and 5, but I don't write those twice. If two sets have the same type of element, you only write it one time. But it's everything that's in A, or everything that's in D, or everything that's in both. What do A and B what do they have? The union of those two, well, they are identical sets, so they have every single set in common. And then between C and D, well, C is an empty set, so it's basically all the elements that are in D that you would list out. Hopefully you guys did okay with that. And excuse my curly brackets, you know, sometimes they're good, sometimes they're not. Complement. Complement is another vocabulary word. The complement of a particular set, which is denoted with an apostrophe type. So you do it like this, or you can do it slightly slanted. Do not do it like so. This means something different. Okay, this means something different. Okay, so try to give it a little bit of curve, or try to make it slanted. Those are the symbols for complement. And complements are basically everything that's not in a particular set. Okay, so this right here will be an example of a complement. It's everything else in the universal set except set A. So everything that does not lie in set A. Okay? Now complement is can be tricky, so I want to show you two other examples. The one up here that's in the white box, the white universal set box, and has only A shaded. Okay? Now this one, like I said, this one can be a little bit tricky. Okay? Because you're trying to basically say everything that's not in B and everything that's not in the universal set, okay? And so there are different ways to write this, but the most simplistic way to write this would be A intersection B complement. Because you want everything that's not a part of B and everything that is in A and where they intersect. So if I drew these things out separately, I'm going to do it right here, okay? Kind of watch what I'm doing, all right? Everything that's not in B, I'm going to shade it with this neon green color. Everything that's not in B is what you see shaded in the neon green color. Okay? And then you want set A. Well, set A is everything that's in yellow. The intersection between the two is where the two colors overlap each other. And as you can see, they overlap each other right here, right in this general region, which is what the white universal set box shows you. Over here in the red, this is an example of everything but the intersection of A and B. So remember, the intersection of A and B is what they had in common, that little inside part. So it's everything that's not in that intersection, which is everything else. We're going to practice this, okay? Let's take a look at this example. We have a universal set, 4, 5, 6, 7, 8, 9, 10. We have set F, 4, 5, 6, 7. We have set G, 6, 7, 8, 9. We're going to draw a Venn diagram for all three sets. So let's start with that before we write down the sets for the other ones. So of course we have our box for our universal set. Is G a subset of F, or is F a subset of G? Hopefully you said no, because there are some elements that are in F that aren't in G, and there are some elements in G that aren't in F. So these are going to be just two circles that intersect each other, because they do have some things in common, but not everything. So what do the two circles have in common? Well, they have the numbers 6 and 7 in common, so we write that in the intersection. That's what they both have. Okay? Now, what's in F? Well, in F, we have just 4 and 5, and then in G, we have the numbers 8 and 9. So we took care of F and G, but let's look at the universal set. Do we have all the numbers in the universal set? No, we don't. 10 is the only number that's not a part of F or G, but is still a part of the universal set. So try to write down what the elements are that are a part of these three sets. So remember that F complement is everything that's not in set F. So all the numbers that are in set F, you don't want to include those, but all the ones that are not a part of that. So that will be the numbers 8, 9, and 10. Because all those are outside of the circle that's F. Now on this one, you want the intersection between F and everything not in G, okay? So if I drew this out really, really small, okay, so you kind of can see this a little bit better, right? Everything that's not everything that's in F, so that'd be this circle, and then everything that's not in G, which would be what's in the yellow, and then you want the intersection, so where they overlap is this right here, okay, just like that last example with the complement. So what numbers are in that particular region? Well, that's 4 and 5. See how that works? Hope so. Okay. Now the next one is the intersection of F and G and everything not in that. Okay. Well, that would be 4, 5, 8, 9, and 10. That would be those particular elements. And if you're like, how? Well, remember, you want everything that's not in the intersection. Okay. So this is the intersection. So you want everything that's not in that intersection, which would be everything that's outside of this general area. So that's everything but 6 and 7. All right, let's take a look at this one. We have a Venn diagram, and each dot represents an element. We want to write down N of G, N of F, etc., etc. Now, what does the N mean? Look, think back to the vocabulary we talked about. N represented the number of elements. So remember the example that we had before. A had 5 elements, B had 4 elements, G had 7 elements. So we're looking here. How many? So basically, it's asking how many dots are in G. Well, there are 2 dots in G. Simple enough. The next one is asking you N of F. How many dots are in F? Well, here's all of F. And even though G lies in F, G is considered a subset of F because all the elements, and actually, wrote that wrong. All the elements in G are also in F. So you can include the dots that are in G because they are in F. So how many dots is that? That's 6. Now the next one is the number of elements in everything that's not in H. Well, here's H. How many dots are not in H? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Try to do the next 3. Okay, try to do the next 3. Pause the video and try to figure out how many elements are in E, F, G, and H. Sorry, how many elements are in E and F, and then determine if the statements in G and H are true or false. Number of elements in the intersection of F and H. Well, F and H intersect right here. How many elements are in that one? Just 1. And then the number of elements that are in the intersection between G and H. Do G and H intersect each other? No, they do not. So because they don't intersect each other, they don't even have any elements in common. Now the ones at the bottom is asking if these statements are true or false. It says the number of elements in the union of F and H. The union. That means what do F and H, how many dots are in F and also in H and also in both? Well, that's 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements in the union between the two. We have to see if the number of elements in F plus the number of elements in H actually equal 8. Well, we already know that there were, how did I skip this one up here for B? There are 6 elements here. And I missed, I jumped the gun, guys. I'm sorry. Let's take it back up here, okay? There were 6 elements in F, and I think I put the 6 in the wrong spot. The number of elements in the intersection of G and F, that was just 2. So my apologies there, okay? Going back to the one at the bottom. The number of elements in F, there were 6 of them. The number of elements in H, you can count, there are 3. 3 plus 6, is that 8? Sure isn't. So this is a false statement. Look at the next one. It says the number of elements in the union between G and H. The union, so that's all the elements that are in G, all the elements in H, and all the elements that are in both. Well, there are 2 elements in G, there's 3 elements in H, so that's a total of 5. So again, there's 2 in G, 3 in H, 2 plus 3, is that 5? Sure is. So that's a true statement. Hopefully I didn't confuse anybody because I did something whatever with B and C. And the last one. This concept can be applied to 3-set Venn diagrams. Okay, yes, you will be doing 3-set Venn diagrams. But the same concept applies. What I like to do is, if anything trips me up, I just like to shade everything and then see either what they have in common, where they overlap, practice with this on your homework. So shade the region on the Venn diagram that shows the sets. Parentheses, just like order of operations, you start with those first. It says the union of A and B. So I'm going to shade the union of A and B. That's basically what A and B, that's all of A, that's all of B, and all of what they intersect. Does everybody see that? And now I'm going to shade C, because that's the next part. So I'm going to shade C, all of C. Now between the yellow and the green, I want the intersection. That's what this symbol right here means. So where do the two colors overlap each other? Well, they overlap each other right in here. So my answer is the pink. So if I were doing this on a test, I would like erase the yellow and erase the green, or I would kind of do like a separate individual box to do the individual shading, and then use the box that they give me as my answer box, where I'll put where they overlap. And then that extra additional box that I would draw in, that would be my work for any method points possible. Now let's look at the next one. I need to shade A. So all of A. Doesn't matter if A intersects with B or whatever, it's A. All of that's A. And now I need to shade the intersection between B and C. B and C intersect right in here. So I'm going to shade that in neon green. And this time between the yellow and the green, I want the union. Union means everything that's in A, everything that's in the intersection of B and C, and everything that's in both of them. So my final answer is actually this whole area between the two. Okay? All right, so that's just the first part of sets. Just kind of making sure everybody understands the concept, the vocabulary, the general theory behind it. We're going to be working on some problem-solving examples the next time, okay?